In our last video, we talked about determinants and how they were a way to take square matrices like a 2x2 grid or a 3x3 grid and take them from a bunch of different values into a single value. And we sort of only loosely talked about how to actually utilize those and said that we were going to use them for the purposes of solving a system of equations. That's what our focus will be in this video. Using determinants through what's called Cramer's Rule to get solutions to a system of equations. Now, a quick recap here. A determinant, more or less, would be, say we had a 2x2 matrix like A, B, C, D, would be a way to take all of those four values and compute a single value from it. And the way that we did this is by getting the product of the first diagonal, so A times D, and then subtracting the second diagonal, so B times C. And we had a process for this as well for the 3x3 grids. And more or less the way that this one worked is we would start with the first value in the first row, cancel out the elements in the same row and same column, and find the determinant of the matrix of the elements that were remaining. And so in total, that would look like A1 times B2 times C3 minus C2 times B3. Minus, then move over to the second value in that row, B1, and say B1 times the determinant formed by the values that aren't in the same row and column as B1. So A2 times C3 minus C2 times A3. Plus, and then move over to the third value, C1, and repeat the same process. We have four values remaining here, and if we were to take their determinant, it would be A2 times B3 minus B2 times A3. And so now the question is, how can we take those determinants and use them to solve a system of equations? And so this process is called Cramer's Rule, and we'll start with the 2x2 version first. Let's say that we were given a system of equations. So if, say, A1 times X plus B1 times Y was equal to C1, and A2 times X plus B2 times Y was equal to C2, right? If this was our system of two equations, we could get these solutions to this system by forming determinants based on the coefficients of X, the coefficients of Y, and the constant term C. Now, for both X and Y, these are going to be fractions, and the denominators of both will be the same. The denominators of both will be the determinant of the four coefficients of X and Y. So A1, B1, right, the coefficients from our first equation in the first row, and then A2, B2, the coefficients of our second equation in our second row, keeping the X's all in the first column and the Y coefficients all in the second column. And that's going to be the determinant of the denominator for both the solution of Y and X. The numerator is going to be very similar, except in the case of X, instead of A1 and A2, right, the ones that are the coefficients of X, we'll replace those X coefficients with the values C1 and C2. And so here we'll have C1 and C2. Likewise with the Y, instead of the coefficients of Y, so instead of B1 and B2, we'll use C1 and C2 there as well. And if we compute all of that, those will give us the numeric solutions, the numeric values that we can plug in to X and Y that make both of these statements, both of these equations true at the same time. And again, this will feel like a lot of steps at first. It will feel like a lot of work. It might even feel a little bit more tedious than doing it by substitution or doing it by elimination. But the reason that this method is so valuable is because computers can handle these lists of numbers really, really well. That's sort of the way that they're designed. And so a process like Cramer's Rule and using determinants is something a computer can do very fast, very rapidly with very large data sets, really, really effectively. And so it's worthwhile to understand that process. But let's see if we can try this on an example. Let's say we have the system 5x plus 4y equal to 12 and 3x minus 6y equal to 24. So really quick, what we can do is start to just label these coefficients, right? A1, B1, and C1 to represent the coefficients of our first equation, and then maybe A2, B2, and C2 to represent the coefficients of our second equation. And then from there, we know that x is equal to the determinant of C1, C2, right? We're gonna replace the x values, the x coefficients, B1, B2, divided by the determinant of A1, B1, A2, B2. And similarly, the solution for y, the value for y, is going to have that same exact denominator, right? So A1, B1, A2, B2, and then have a similar numerator, just instead of replacing the x coefficients like we did for the x solution, we're going to replace the y coefficients. And so we'll have A1, C1 and A2, C2. And so all that's going to be left for us here in order to get these solutions is just to compute all of these determinants and do the division. So let's start with this first one up top. We have C1, B1, which in this case is going to be 12 and 4. Just pulling these again from these equations here, their coefficients. And then C2, B2, which will be 24, negative 6. If we do this determinant, we want to take the product of this diagonal, so that's going to be 12 times negative 6, minus the product of this diagonal, 24 times 4. 12 times negative 6 is going to be negative 72, minus 24 times 4, which will be minus 96, which when we subtract gives us negative 168. Our denominator is going to be A1, B1, or 5, 4, and then A2, B2, or 3, negative 6. And so doing this determinant is going to be taking the product of the first diagonal, so 5 times negative 6, minus the product of the second diagonal, which will be 4 times 3. 5 times negative 6 is going to give us negative 30, minus 4 times 3 would be minus 12, and so this will be negative 30 minus 12, or negative 42. And finally, reducing this fraction of negative 168 divided by negative 42. First of all, we've got two negatives, so that's going to make this positive, but then 168 over 42 is just positive 4. And so we've found the x value of our xy solution pair. We want to do this similarly with y2. So if we look here, we've got a similar denominator, right? A1, B1, A2, B2. And so we know that this is still going to be negative 42 because we've already computed it. This is identical to this. And so because of that, we can just pull that same value. Now looking at the top, we've got A1, C1. So in that case, it's going to be 5 and 12, and A2, C2, or 3 and 24. To take the determinant, we'll multiply the two along this first diagonal, so we'll have 5 times 24 minus the product of this second diagonal, so 12 times 3. And of course, this will still be divided by negative 42, but then we can go ahead and evaluate the numerator. 5 times 24 will give us 120, and 12 times 3 will give us 36. And so we have 120 minus 36, in other words, 84. And 84 over negative 42, this will be negative, but that will be 84 over 42, which is 2, so negative 2. And so this now represents our solution pair, right? It represents the XY pair that satisfies both of these two equations simultaneously, right? And that's the pair 4, negative 2. In other words, if we were to plug both of these into either of these equations, we would find that it satisfies both of them. Now we can try that just to check, right? And so if we look at 5 times 4 plus 4 times negative 2, we should expect to get 12. And if we do this multiplication, 5 times 4 is going to equal 20. 4 times negative 2 will be minus 8. And 20 minus 8 is indeed 12, right? 12 equals 12 is a true statement, and so that confirms that these two satisfy our first equation. We can look similarly at our second to say 3 times 4 minus 6 times negative 2 is equal to 24. And if we do the arithmetic out, we can confirm this because 3 times 4 is 12, and minus 6 times minus 2 is also positive 12. And positive 12 plus positive 12 is equal to 24. And so we're left with a true statement, 24 equals 24. And so this confirms that we were able to do this correctly. And in particular, that the pair 4, negative 2 is a solution to this system of equations. Now, that works really well for a 2 by 2 matrix, but it's actually not so different for a 3 by 3. In particular, if we were given a system of equations, say a1 times x plus b1 times y plus c1 times z equal to d1, and a2 times x plus b2 times y plus c2 times z equal to d2, and lastly a3 times x plus b3 times y plus c3 times z equal to d3, and this was our whole system of equations, then in almost exactly the same fashion, we can compute the values for x, y, and z by using determinants. And just like with the 2 by 2 case, the denominators of all of these will have the same matrix, which will be determined just by the coefficients of the 3 variables. And so in every case here, we will divide by a1, b1, c1, a2, b2, c2, a3, b3, and c3, and take the determinant of all of those. And in fact, what I'll do here, even because this is the same for x, for y, and for z, is I'm just gonna copy and paste and slide that over for each of them. Now the numerators, they'll be a little bit different, but they'll follow that same pattern, right? In the case of x, instead of using the coefficients of x, that's where we'll plug in the d's, the constant terms. Right, so here we'll list the first column as d1, d2, d3, and then use the coefficients of y and z. So b1, b2, and b3, and c1, c2, and c3. And the determinant of that matrix will be the numerator of our x value. Likewise for y, we'll take the determinant of the matrix that uses all of the coefficients, except instead of the y coefficients, we'll replace those with the constant terms. So this will be a1, a2, and a3 in the first column, but d1, d2, and d3 in the second column, and c1, c2, and c3 in the third. And as you might be able to guess at this point, the z will be a1, a2, a3, b1, b2, and b3 across the first 2 columns, but then the third, the coefficients of z, will be replaced with those constant terms d. And so we'll have D1, D2, and D3. And so let's see if we can apply this to an example here as well, where we're given a system with three equations, namely 3x minus 2y plus z equal to 16, 2x plus 3y minus z equal to negative 9, and x plus 4y plus 3z equal to 2. Now we know that for each of these we're going to need to compute that same denominator, that denominator of a1, a2, a3, and b1, b2, b3, c1, c2, and c3, the determinant of this matrix here. And so let's go ahead and do that now so that we can then utilize it for x, y, and z. So this would be taking the determinant of, in this case, if we look at our coefficients, we'll have 3, negative 2, and 1 coming from 3, negative 2, and 1 up here, the coefficients of our variables. We'll have 2, 3, and negative 1 for our second row, so 2, 3, and negative 1. And then finally 1, 4, and 3 for our third row, 1, 4, and 3. To take the determinant of a 3 by 3, we'll start with our first term, 3, and multiply that by the determinant of the 4 that remain. So multiplying this diagonal here, that gives us 3 times 3, minus this diagonal here, so minus negative 1 times 4. And then we'll subtract. We'll look at our second term here. So that will be negative 2 times the determinant of the matrix formed by these four values. In other words, the product of this diagonal, 2 times 3, minus the product of this diagonal, negative 1 times 1, and then plus our third value here, so 1, times the determinant of this matrix here. In other words, the product of 2 times 4 minus the product of this diagonal, 3 times 1. Doing our arithmetic, that's going to give us 3 times 3 times 3, which is 9, minus negative 1, which will be positive, times 4, so plus 4, and then minus negative 2, or simply plus 2, times 2 times 3, which gives us 6, minus negative 1 again, so that's going to be plus 1 times 1, so plus 1 here. And then we have plus 1, since this is just 1 times this whole bit in parentheses, I'm just going to leave that part out here. We've got 2 times 4, which is 8. We've got minus 3 times 1, which is minus 3. And then we can simplify this a little bit further. 9 plus 4 gives us 13, and so we have 3 times 13. 6 plus 1 gives us 7, and so we have 2 times 7. 8 minus 3 gives us 5, and so we have plus 5. Or in other words, 3 times 13, which would be 39, plus 2 times 7, or 14, plus 5. 39 plus 14 gives us 53. 53 plus 5 gives us 58. And now this would represent our denominator of all three of our variables, x, y, and z. And so we're going to take this value and hold on to it for later. And now from here, we'll want to look at the specific determinants for x, y, and z. And so we'll have x is equal to the determinant of replacing the x coefficients with our constants. That's going to give us 16, negative 9, and 2 down the first column. And then exactly the same in the other two. We've got our coefficients of y here, so negative 2, 3, and 4. And our coefficients of z here, or 1, negative 1, and 3. And that result would be divided by 58. Similarly, we would have y as the determinant of 3, 2, 1, right, the coefficients of x. Then instead of the coefficients of y next, we would replace that with the constant terms, so negative 16, negative 9, and 2. And then the coefficients of z, so 1, negative 1, and 3. And again, dividing that result by 58. And lastly, z would be equal to 3, 2, 1, the coefficients of x down the first row, -2, 3, and 4, the coefficients of y down the second row, and 16, -9, 2, the constant terms down the last row, replacing the coefficients of z. And again, divided by 58 to give us our z coordinate. Now, because this will take us a lot of time to work through on video, and I've already demonstrated this in a few examples, I'm going to skip the full explanation of evaluating each. It's going to follow the same process as the 3x3 determinants we've done so far, but at least to save us some time on the video, I'm going to compute those separately and then jump back in. So this first one here for x, if we evaluate the determinant listed here in our numerator, that's going to come out to 116. And of course, again, divided by 58 for our denominator. I would encourage you to work through this and check on it yourself to make sure that you're getting the same answer, but this will come out to 116. Similarly, the y value will come out to -174, again, divided by 58. And the z value will come out to 232, again, also divided by 58. Now, simplifying these, 116 over 58 is equal to 2. -174 over 58 would give us -3, and 232 over 58 would give us 4. And so we can say, therefore, the solution of 2, -3, 4, right, that triple of x, y, and z would satisfy each of these three equations. If we were to plug in these three values to any of these equations, we would find that the statement is true. And so now we can utilize some of the tools from linear algebra or matrix theory to help us solve systems of equations. It's another tool in our toolbox, right? In addition to substitution and elimination, we can utilize Cramer's rule and determinants to get to our solutions as well. And in particular, a tool that's really useful if you ever need to work with programming a computer to solve these types of problems automatically. Now, of course, just like the previous methods that we've used to solve systems of equations, there's lots of little computations along the way through these processes. And so it is really worthwhile to, number one, get a lot of practice, but number two, be as deliberate as you can with the details. But of course, with practice and with a focused attention to detail, you now have multiple tools at which you can solve these types of problems. I hope you found this interesting, and I hope it's helpful in terms of solving for systems of linear equations. If you do have any questions, please reach out and let me know. Otherwise, I hope you have a great rest of your day.